Yeah, right. Good. Good morning, my dear students. Good morning. Nice to meet you all. Okay. For today class, just I will go to the presentation. Right. Yeah. This one, where is that? Yeah. Yeah. Actually, please listen here. Approximate method, I told you, three approximate method. One is functional approximation. Next one is finite difference method, then finite element method. That functional approximation method, we use Rayleigh-Ritz method. Okay. Rayleigh-Ritz method. And then finite difference method, then finite element method. Actually, this finite element method uses the best features of the above two method. The other two approximate method, what are they? Functional approximation, that is Rayleigh-Ritz method, and finite difference method. There are certain best features available in that. No, that is well utilized. It combines the best features of those two methods. Is called finite element method. Okay. So what is the best feature we take from finite difference method? I told you in your syllabus you don't have finite difference method. That's why I skipped it. Okay. The previous pages of finite difference method, whatever I have discussed in detail, that I have skipped it. Okay. Now, which best feature finite element method utilizes? Abdina, this paragraph lastly I have written. However, the concept of discretization used in this method, which method? Finite difference method, formed the basis of the finite element method. So the concept, okay, of discretization is formed the basis of the finite element method. That is the best feature. The discretization concept is the best feature of finite difference method. That is used, that formed the basis for our finite element method. Okay, that alone you keep it in mind. Now I am going to functional approximation called Rayleigh-Ritz method. Okay, one of the method. There are several methods of functional approximation, out of which the Rayleigh-Ritz method is familiar. That's why I am going to teach you Rayleigh-Ritz method, because this potential energy formulation for numerical solution, this is there in your syllabus. That clearly shows I have to teach you Rayleigh-Ritz method. Okay, good. So before discussing this, right, just I will start from here. Yeah, here what is written? Governing functional approximation. The heading here is governing the first method. Okay, the first approximate method, governing functional, or that is nothing but functional approximation method. Okay, functional approximation. I want to have some discussion here. What is we do in functional approximation? A set of independent functions satisfying the boundary conditions is chosen. A set of independent functions, okay, satisfying the boundary conditions is chosen, and a linear combination of finite number of them is taken to approximately specify the field variable at any point. Right? For example, you take a beam problem. The field variable is deflection along the length of the beam. That is the field variable. To represent the deflection, we choose a set of independent functions satisfying the boundary condition. Which boundary condition? Both kinematic and static boundary conditions. Okay. And a linear combination of a finite number of them is taken to approximately specify the field variable at any point. Okay. When you combine the linear combination of that chosen function is done, the finite number of functions are done, we use some unknown parameter, coefficients, called coefficients, unknown parameter in it. Okay. The unknown parameters that combines the functions, okay, are found out in such a way to achieve. Now we have to determine the value for that unknown parameter which combines a set of independent functions. Okay, the functions are found out in such a way to achieve at the best field condition. So we have to find out its value to achieve at best the field condition, which is represented through variational formulation. Later it is represented. We choose some governing functional. The linear combination of them and all I told you, no, which is nothing but a governing functional, okay, or solution, whatever it is, that represents the field variable very well. That finally, which is represented through variational formulation. Later, some variational formulation we do, some function formulation, governing functional formulation we do, some function. Okay, that is variational formulation means its derivative must be 0, something like that. We are going to do it. Okay, and its derivative, that is called variational formulation. Let us see. The well-known classical methods, see, remember, the well-known classical, very old methods they are. That's why the well-known classical methods such as Rayleigh-Ritz, Galerkin and collocation. Please keep it in mind, Galerkin sometimes, there is another method called Galerkin and collocation, are based on functional approximation. Okay, the classical methods are Rayleigh-Ritz method, excuse me. Okay, and the Galerkin and collocation are based on the functional approximation. The Rayleigh-Ritz method is described here. Rayleigh-Ritz method is described here. Okay, so I will do governing functional, governing differential equation, that is equilibrium approach. Next, I am going for another approach called energy approach. In that, this functional approximation, this Rayleigh-Ritz method, Galerkin collocation method are there. We are going to discuss Rayleigh-Ritz method. Now I will come to the title here. That's why sometimes in the syllabus you found potential energy formulations for numerical solution. Potential energy formulation. That is energy approach, energy method. Governing functional or functional approximation. These are the word. Okay. Best method is Rayleigh-Ritz method. Potential energy formulation for numerical solution, Rayleigh-Ritz method. Okay. Before going to discuss with you the Rayleigh-Ritz method, right? Here I want to just the same topic. Otherwise, okay, no problem. Before going to discuss with you, I must tell you what is potential energy. Okay. What is the principle of stationary potential energy? How do we obtain the maximum potential energy, extremum value or maximum value of it, stationary value of it? I will discuss now. First of all, please, already last class I told you what is maybe potential energy now. If you take any structural system or deformable bodies, if you take any structural system or deformable bodies, the potential energy is found out this way. The potential energy is the capacity of the forces to do work. In general, potential energy means capacity of forces to do work is potential energy. If you take our structural system, or because we don't treat it as a rigid body, here we don't have a rigid body concept, mechanics of solids. No, when we deal with the bodies, solid bodies, elastic bodies, okay, deformable bodies, there it has external forces as well as internal forces. I told you potential energy is the capacity of the forces to do work. Okay. Now, external forces due to loads and internal forces due to stresses or stress resultants. Okay. It is there in the body. So, the total potential energy is the work done by the external loads plus the work done by the internal forces like stresses and or stress resultants like bending motion force, whatever it is. Generally say stresses. This is the total potential energy. Okay. Now I am coming to the principle of stationary potential energy. Principle of stationary potential energy. I am using the word stationary. Principle of stationary potential energy. Stationary means it is stationary. Okay. After achieving extremum value, the potential energy is stationary. That's why it is stationary potential energy or extremum value. Extremum or stationary potential energy. Okay. If you take any deformable bodies, why a body deform? Under the action of external load acting on it. When it deforms, it's elastic body. No, there are internal forces set up in that. If you remove those forces, the internal forces do work and take back this body to its original static position. That's why it is called elastic body. You know all this fact, right? Now, what I want to say, when the body is in equilibrium position, it deforms. Okay, when a body is subject to loads, it deforms. Is it keep on deforming? No, it deforms. Then it come to it is stationary now. Okay, by extremum. It means the total potential energy attained a extremum value, a stationary value. Okay, when things so, how do you get something attained extremum value or a stationary value? How do you get it? Its variation must be zero. In other words, its derivative must be zero. Variation means derivative. Differentiation. That's the differentiation must be zero. First derivative must be zero. Okay. Because in any curve at a peak, the slope is zero. No, its derivative is zero. Its variation is zero. That is called a variation. Okay. variational must be 0, or derivative must be 0, its first derivative must be 0, that is slope must be 0. Using this concept, we can do something. We can evaluate the unknown parameters which combine the various function. Okay, let us see. Reliance method is one such method. Okay, whatever I discussed, I have given notes here. See here, governing functional, variational formulation, functional approximation, Rayleigh-Ritz method. This energy approach. Okay, potential energy is the capacity of the forces to do work. For structural system or deformable bodies, the forces are classified as external forces due to loads and internal forces due to stresses or stress resultants. Okay. Thus, the total potential energy is the sum of the potential energy of the external and internal forces. Okay. Then now I have written principle of stationary potential energy. Total potential energy is equal to potential energy due to internal forces plus potential energy due to external forces or loads. Okay. That rotation used is pi. This kind of pi. Psi in solar, it's also psi. Some psi type. Okay. Is equal to u plus h. Right? It's not the pi used by us in mathematics. It's some psi type. Okay. Is equal to u plus h. U is the internal work. Okay. Internal work done. H is the external work done. Right? Is the internal work done. H is the external work done. U plus h. Now I am coming to the principle of stationary potential energy. If a demovable body or structural system is in equilibrium, the total potential energy of the system has a stationary or extremum value. Has a stationary extremum value, right? The system has attained a stationary or extremum value. The total potential energy of the system, the total potential energy of the system has attained stationary or extremum value. That's the meaning. That's the principle of stationary potential energy. The extremum or stationary value of the functional is obtained by equating the first variation. What is mean by variation? Derivative, differentiation, okay, of the function to 0. Dou pi, psi or pi, whatever it is, dou psi divided by dou of that parameter, whatever parameter you use, whatever variation notation you use, there is small a or x or whatever you use. That's why I put dash here. Is equal to 0. It's okay. This way you have to determine with respect to that variable. Okay, partial differentiation of with respect to the variable, it must be 0. You have to do it. This much sufficient. Okay, I have written what is potential energy, what is principle of stationary potential energy. Please, I advise you to prepare your notes. Okay, play the video later and prepare notes in your own by referring the video. Right? Okay, I will come to our continuity of this one. Actually, it's not neatly written, no problem. It's what's written long back in a very tragic situation. I told you, right? Right after brother death, it was prepared. This note was prepared. Several occasions I told you. Okay, just start with analyze a simply supported beam subjected to UDL of intensity P suffix naught, P naught. Okay, so I have a simply supported beam subject to UDL. Say the intensity of the load is P suffix naught. Normally, in practice in structural mechanics, you all familiar with W, small w, isn't it? But here the notation used is P naught. The reason is I referred Krishnamurti textbook. In Krishnamurti textbook, yes, yeah, Rayleigh method, I referred to Krishnamurti textbook, I think. Yeah, this problem is from Krishnamurti, T.S. Krishnamurti. So he used P naught per unit run, okay, the UDL intensity. At a distance x from one end, one support, say the deflection is small w. Since the author has used the small w to represent the deflection at any point and P naught to represent the intensity of the UDL. I also used the same thing. While referring that Professor C.S. Krishnamurti textbook, you should not get confused. No, that is why in my notes I used the same notation. Now we are coming to the governing functional. Okay. First, what we do, we are going to get the governing function. First, we are assuming the field variable, the deflection. What is the field variable here? The deflection along the length of the beam. The small w is the field variable. First, I am going to assume the field variable. For that, we call it as trial function or displacement function. Trial function or displacement function I am going to choose. Please listen here. This is the concept of this method. It is used in a Van-Dierman method. The trial function. Okay, the concept of using trial function is used there. Very good. The trial function may be anything. It may be a trigonometrical function or algebraic polynomial function or even exponential function. Okay, no simple guidelines available to choose such function. All of you remember, no simple guidelines available to choose such a function. Mathematics have suggested certain function. Okay, based on experience, we are choosing this one. Okay, let us see. Either you can go for trigonometrical function with the one-term approximation, algebraic polynomial with the one-term approximation. If you want to more accuracy, you have to go for more terms. Trigonometrical function with the one term or combination of two functions, two terms, combination of three independent functions, three terms, which will combine them with unknown parameter. Okay, or algebraic polynomial with the one term approximation or two term, three term you can go. For simplification, I started with the one term to tell you the method. Okay, more number of terms are there. If you choose more independent functions and combine them with unknown parameter, okay, your solution will be go to accurate, but computation will be somewhat complication. Okay, no problem. Just I am start with the one term approximation, right? It's approximation, one term. Trial function I am first choosing. Trigonometrical function I am choosing. I am choosing W equal to A sin pi x by L. I have chosen a function like this. To choose such function, please all of you keep it in mind. No simple guidelines available. It is chosen by the mathematics based on their experience. Okay, W equal to A sin pi x by L. How this chosen function, whether it is satisfies the field variable. What is the field variable here? W. What is the field variable here? W. What is the value of this W at A at this point? 0, differential 0. What is the value of W here? The field variable value here? 0. Okay, field variable, which is also called kinematic boundary condition, right? That is a different question with this one. The field variable. This chosen function satisfies the field variable. How? If you put x is equal to 0, W becomes 0. If you put x is equal to L, L by L. So sin pi, what is the value of sin pi? Sin n pi 0, no? Am I right? Okay, 0. So it satisfies, this function, chosen function satisfies the field variable. We have to check whether it, I'm not sure, it's okay. Field variable, so whether it satisfies. Whether it satisfies the boundary conditions, we have to check. Okay, so what I have written here, I have written the differentiation of it. dw by dx, strictly speaking, I should have written here, but however, I have written at the corner here. It's okay, no problem. At the edges here. dw by dx is equal to, its derivative is equal to a into pi L, okay? Pi L into cos pi x by L. It's not visible here, cos pi x by L. Next, it's further derivative. D square W by dx square is equal to further derivative sin to cos, then minus sin, no. That's why minus a into pi by L. Already one pi by L is there. Another into another pi by L. So pi by L whole square into sin pi x by L. Okay, these are the derivative twice. Okay, it is there. Now I am checking the boundary conditions are for the chosen trial function. I am verifying the boundary condition. At x is equal to 0, W equal to 0, no doubt. At x equal to 0, the kinematic boundary condition is 0. And also field variable. You can say field variable also 0. So the chosen function satisfies field variable as well as kinematic boundary condition. And EI d square by W by dx square is equal to M minus M. You know, EI d square W by dx square equal to minus M, which is 0. Where at x is equal to 0, the semi-supported end bending moment is 0. So this function also satisfies that. Where is that? What is d square W by dx square here? In that, if you substitute x is equal to 0, your sin pi x by L becomes 0, no? So everything becomes 0. So it's satisfied. At x is equal to L, substitute x is equal to L in it. So sin pi 0. Okay, sin n pi is 0, no, always. Okay, at x is equal to L, W equal to 0. Field variable is 0 or kinematic boundary condition 0, you can say W equal to 0. And EI d square by dx square equal to M minus M. Say minus M. At this end also, simply support end also, bending moment 0. In this, you substitute x is equal to L, so you will be getting sin n pi. Only sin pi you will be getting at the end. That becomes 0. Satisfies. And another satisfaction also we are checking. What is that? At x is equal to L by 2, dy by dx I am getting. See, dw by dx. dw by dx, substitute x is equal to L by 2 here. That also becomes 0. Symmetry condition. Okay. That is at the center. Due to symmetry, the beam bends nicely like this. The deflection is maximum at the center. Here the slope is 0. That also the chosen trial function has satisfied. Okay, please, no problem. Strain energy stored. Excuse me, sorry. Strain energy stored, right. Now I am coming to our discussion here. Strain energy stored. U equal to, see here. Oh, no, I will come to that later. What is this strain energy stored? In that beam, you consider a small infinitesimal element dx. Okay, small element dx you consider. Okay, what is the strain energy stored there? Already you know the formula. The strain energy stored is m square dx divided by 2ei. This you have studied in your mechanics of solids. Okay, basics mechanics of solids. The strain energy stored due to bending, strain energy stored due to torsion, strain energy stored due to shear, and all you studied. Okay, the strain energy stored due to bending is m square divided by 2a into dx. This already you have studied. Okay, that is for infinitesimal distance of dx. For a whole length 0 to L length of the beam, you have to do integration of this one. So the integration is, integral limit is 0 to L, u equal to, okay, the internal work done is equal to 0, integral 0 to L m square divided by 2a into dx. Okay, m square divided by 2ei into dx. Now you substitute this m square value is known to you, which is equal to, what is m? Okay, what is the m here? M equal to ei d square w by dx square, maybe with the negative sign, but m square only you are going to substitute, so the negative sign will go. M equal to minus ei d square, because ei d square w by dx square equal to minus m, therefore m equal to minus ei d square w by dx square. Since m square, this will go. Okay, so ei square already ei is there, one ei is here, the denominator, that's why ei alone is there. Okay, right, divided by 2, this 2 is there, no, this 2 comes here, so ei divided by 2, integral 0 to L, only this d square w by dx square whole square is there into dx. Okay, m value I have substituted, this m value I have substituted here. Still I have not substituted this d square by dx square value. It is available here for chosen function. Let us substitute as the next step. Now I am substituting u equal to ei divided by 2, this is there, integral 0 to L. Okay, this d square w by dx square, what is that? It is written here. What is that? D square, not ei, only this d square w by dx square. What is that? That is here, d square w by dx square equal to minus a into pi by L whole square into sine pi x by L. Okay, that you know. That is why if you substitute minus a, okay, pi square by L square into sine pi x by L. This is whole square, because d square w by dx square whole square is there, no, that is why square into dx. Okay, now since I have written here, since d square w by dx square is equal to minus a pi square divided by L square into sine pi x by L. Okay, so we have substituted this value here. Now expand it. All right, so ei by 2 into 0 to L a square, this minus become plus now. Okay, minus a square, which if you square it, plus a square, and then pi square is there, if you square it, pi power 4 L by 4. Okay, sine pi x by L, if you square it, sine square pi x by L. Okay, into dx. If you want, you can put bracket, no problem. You can, if you want, you can put bracket. Okay, no problem. Now that is equal to ei by 2 into these and all constant, a square, pi square, L power 4 and all constant, a square, pi square divided by L power 4 constant. So we have taken outside this one. So integral 0 to L, this is the function, only variable. Okay, sine square pi x by L into dx. Okay, this you have to integrate. How do you integrate? Sine square pi x by L. Okay, we have your expression already. Sine square ax equal to anything, some formula, maybe A or some other notation you might have studied in mathematics. Sin square AX is equal to, if you want to get it, 1 minus cos 2AX divided by 2. Okay, if you integrate it, integral sin square AX is equal to, you integrate this, what is this? 1 by 2. That is why x by 2. First, this is 1 by 2, no? So 1 by 2, if you integrate, x by 2 minus, this is cos 2ax by 2, no? You integrate it. Sin 2ax divided by this 2a come to denominator. Already 2 is there. 2 into 2a, 4a. Okay, this is the one. So this formula I have written, its integration value also I have written. Likewise, you have to integrate this. Okay, integrate it. U equal to ei by 2, please ei by 2, a square pi power 4 by l power 4 into this one. Integration of this sin square pi x by l. Its integration is with reference to this formula. You have to do it. X by 2 minus sin 2 pi x by l, 2 pi x by l divided by 4 pi by l. Okay, 4 pi by l. Right, with reference to this 4 pi by l, 0 to l. Please you apply your mind. Shall you think? This formula I have written because this sin square pi x by l required to be integrated. So from this formula we have done the integrated value here. Okay, that's what. So for u equal to ei by 2 into a square pi power 4 l power 4 into, if you apply upper limit and lower limit, upper limit, okay, first apply minus first apply upper limit l by 2. Apply upper limit here, this LL get cancelled. So it becomes sin 2 pi, sin n pi is 0. So this value becomes 0. Only L by 2 is there. Next, if you apply 0 value, if you apply x equal to 0 minus lower limit, no, lower limit 0, if you substitute 0. If you substitute lower limit 0 here, 0. That's why L by 2 alone is there. Okay. So therefore, U equal to EI pi power 4 divided by 4 L cube. Okay. Because this L is there, here L power 4, L cube it becomes, okay. The here one 2 is there, that 2 into 2, 4, pi power 4, a square is there, a square I have taken here. Because in my expression, the a square is the variable. My intention is to determine this unknown parameter. Please, all of you here, listen here. The chosen function is, chosen function W equal to a sin pi x by L. Sin pi x by L is the actual function. Okay. A is a coefficient. A linear combination. If I want to have another function here, I have to write it down plus b into that function, sin some 3 pi x by L, something like that. Okay, that's what. These our main intention. Why we do this functional approximation using some concept, energy concept, to evaluate this unknown parameter A. We do all this business to evaluate some the value of the A here. You will enjoy it later. Just to listen. How we get this way, that way. These are the concept, okay, concept of the subject. So the internal work done, okay, the work done by the internal forces, the work stresses. Internal forces means the stresses. Okay, the internal forces is obtained as EI pi power 4 divided by 4 L cube into A square. Okay, my intention is to determine the value of A, some expression for A, that we will do it later. Next time I am coming to, I will finish. This I will stop. Okay, next I am coming to potential energy due to load. Okay, H. Potential energy due to load H. Load. Okay, we use the rotation H is equal to minus P into del. Due to load, what is the work done? Load force into displacement. No, that's why minus 4 P into del. Force into displacement. Why negative sign? Actually, the internal forces tends to take back the beam to its static equilibrium position, while this loads tends to displace the beam away from its static equilibrium position. Okay, since the loads tends to displace the beam away from its static equilibrium position, it is negative work done. Okay, that is why it's a negative work done. Okay, so H equal to minus in that beam. I want to show you that beam, you take a small infinitesimal distance dx. What is the load here? P naught into dx. P naught into dx is the force load for a infinitesimal distance dx. 30 into the deflection there, W. Okay, say the deflection there is small w or something, right? That's what written here. Where is that? it's W into P naught into dx, P naught dx into W. This is supposed to be written as, please see here, the work done by force acting over infinitesimal distance dx is P naught into dx is the force, is the total load for that infinitesimal distance dx into W, the displacement below it. W is the variable here, W. Okay, P naught dx, W I have written, P naught W into dx I have written like this. This is for infinitesimal length. For entire length of the beam, what to do? I have to integrate. Okay, 0 to L, that's why minus 0 to L, P naught W dx. Okay, now you integrate it. That is equal to minus 0 to L, P naught W dx is equal to minus 0 to L, P naught. What is the value of W? We have chosen assumed function, no? A into sine pi x by L, trial function. That W is nothing but W equal to, we have chosen already a trial function. A sine pi x by L. Substitute that one instead of W here. A sine pi x by L into dx. Okay. Now you minus P naught and A are the constant values. So I have written here. Now minus I have to integrate only the sine pi x by L into dx. Okay. Sine pi x by L I have to integrate with respect to dx. Okay. So if I integrate, it becomes sine, if I integrate, it becomes cos. Minus cos pi x by L, denominator divided by differentiation we will multiply. The integration we divide. Okay. Denominator this coefficient of x, pi by L. Okay. Under upper limit 0 to L, upper and lower limit are substituted here. You have to apply the limit later. That is equal to, it is available here. Okay. That is equal to, okay, minus P naught A, already is there, into apply upper limit. If you apply upper limit, LL get cancelled, minus cos pi. Okay, cos pi equal to minus 1. Okay, otherwise, what I have written here, L by pi. Okay, yeah, that's what. See, if you substitute x is equal to L here, L get cancelled. You are getting minus cos pi. Minus cos pi is minus 1. That's why it becomes minus 1 divided by pi by L. Okay, this minus already have taken here. Please see here. The minus available here already taken outside here. Now this is a new u minus sign. How? Because cos pi x by L, x is L. So LL cancelled. Then cos pi alone. Cos pi value is minus 1. So minus 1 divided by pi by L. So L by pi. Minus L by pi. Minus L by pi. Okay. Into apply lower limit. No. What I have done, I am sorry. I'm sorry. What I have done already for the work done by the external forces, minus is there. Okay, already minus is there. No, right from the beginning, minus is there. Right from the beginning, minus sign is there outside. So that minus that is this one. Minus P naught A. Okay, the minus P naught A into this denominator. I have a constant pi by L. That I have taken outside. That is minus L by pi. Here this minus sign is there. No, that's why minus L by pi I have taken outside. Now I am applying upper limit and lower limit for this cos pi x by L alone. Okay, cos pi x by L alone, I am applying upper limit. If I substitute L, cos pi, that is minus 1. That minus 1 I have written here. If I apply a lower limit to the cos pi x by L, I am getting cos 0. So minus of this cos 0, 1. So minus 1. That becomes minus 2. Okay. So finally H equal to already minus 2, minus, again minus only. If I apply minus thrice, I am getting minus only. Minus 2 P naught L pi into A. Okay. The A I have written like this. Okay. Finally, I am getting this work done by the external forces into this form. I am going to finish another 5 minutes. Total energy pi equal to, okay, the pi or psi, whatever it is equal to U plus H. That is equal to, this psi is equal to, already we have this value. You know, work done due to internal forces, this one. That is written here. Okay. Work done due to the external forces we obtained here. Okay. That is written here with the negative sign. Minus, because it's in the negative sign only we are obtaining, I have obtained. Minus 2 P naught L by pi into A. You go through leisurely this one I have explained. Okay. Now this is the function. some approximated function, governing function we have obtained. For what? For the unknown parameter A, in terms of A square, A and all. Okay. Now I'm discussing further. For stable equilibrium of the body of the potential energy attains stationary value. For stable equilibrium of the body, the potential energy attains stationary value. The total potential energy attains stationary value. Therefore, dou pi, its first derivative, its variation, its derivative must be 0. Its variation must be 0. Its derivative must be 0. First derivative must be 0. So, dou pi by dou A with respect to A. Here the variable here is, this is constant, this is constant. The variable is the unknown parameter in our trial function A. Okay. Dou A is equal to 0. So, differentiate this with respect to A. If you differentiate this with respect to A, 2A. Okay, here. So, 2A means this 4 becomes 2. EI pi power 4 divided by 2 L cube alone into A. I differentiated. If you differentiate this with respect to A, only minus 2 P naught L by pi into 1. Okay. So, that's what. Minus 2 P naught L by pi alone. Okay. Because if you differentiate this, only this coefficient you have to take. This is 1. Okay. So, that is equal to 0. From this, please listen. You will be enjoy it. Listen for few more minutes. I am going to finish. Okay. A is equal to, from this I am writing this unknown parameter. A is equal to, okay, you take this LHS side, you take this one, denominator to numerator, numerator to denominator, this side of the equation. So you are getting P naught, after simplification, you are getting 4 P naught L power 4 divided by A pi power 5. Okay. This is the one. Therefore, the trial function, we have approximated a function, no, trial function. Its complete solution, its final solution is, its final expression is W equal to A value you obtained, 4 P naught L power 4 EI pi power 4 into sin pi x by L. Okay, you obtained it. This is equal to W. The final solution is obtained for field variable W, the reflection along the length of the beam W. You have to validate it. No, you got some expression using some concept, energy concept. Now we have to ascertain what you obtained is right or not. You have to validate it. How to validate? Okay, how to ascertain it? Okay, what you obtained is right. Let us see. I will tell you now. Maximum deflection at x is equal to L by 2. You know, in a similarly supported beam, the deflection is maximum at the center. So maximum deflection at x is equal to L by 2. Substitute x is equal to L by 2 in this. So this becomes W max becomes 4 P naught L power 4 divided by 5 power 5 EI. That is W max equal to you 4 divided by pi power 5 compute in the calculator. Okay, or in the numerator, sorry, in the denominator, pi power 5 divided by 4. Bring this one divided by 4. You'll be getting P naught L power 4 divided by 76 EI. Please, all of you listen here. The UDL into L power 4 divided by some constant 76.5 into EI we are getting. Okay, listen, because sin pi by 2 is 1. If you substitute this one here, no, please see here. This is the maximum deflection obtained from this energy approach. Already we have from double integration method or Macaulay's method. Okay, already that is equilibrium approach. Okay, already we have exact solution, exact value we know, exact solution W equal to W max equal to, you please recall 5 divided by 384 into P naught L power 4 by EI. This equation you all know, this expression is well known to you. The maximum deflection, when you are simply supported beam is subjected to UDL, the maximum deflection is at the center, whose value is 5 P naught L power 4 divided by 384 EI. Please don't get confused with this notation. Now you will be using 5 W L power 4. Yeah, instead of P naught, you have used that W. 5 W L power 4 divided by 384 EI. You have used it. So here 5 P naught, the UDL, to represent UDL, you are using the notation P naught. That's why 5 P naught L power 4 divided by 384 EI. What is 384 divided by 5? Bring it down. It comes P naught L power 4 divided by 76.8 EI. Please see here, 76.8 EI. That is the one. This formula, this expression which is well known to you, I have written 384 divided by 5 here. Okay, so P naught L power 4 divided by 76.8 EI. But see, from energy approach, whatever we have done so far, internal work done, external work done, and we first assumed some trial function, and there was the unknown parameter A. To evaluate that unknown parameter A, we have done this much business, this much we scratched our head like anything, this much we struggled to obtain integration, all differentiation, everything we have done. Finally, see, we got the unknown parameter A, then we got the final trial function value. In that, you got W max at secondary value is this much. Okay, see the difference? Here it is 76.5, here it is 76.8. That's all. Exact solution is known to you from a equilibrium approach. You got it. Okay, double integration method, mechanics method, which you have studied in your mechanics of material subject, or basic mechanics of solid subject, whatever it is. Okay, see, now you can enjoy the beauty of it. What is the percentage error involved? 76.8 minus 76.5 divided by 76.5 into 100. That is equal to difference between those two divided by 76.8. 76.8 is the exact value, no? That is why difference between these two and into 100 will give you 0.39% only error involved. Okay, see the beauty of it. Some energy principle you will applied. Okay, stationary principle of stationary potential energy, internal work done, all concepts. See, already we have established concept. We combined them. Finally, we got the same value. See the beauty of it. For stable equilibrium of the body, the potential energy attains stationary value. Okay, that's what, again, the repetition of this one. Okay, other discussion. Okay, I'm finished. And also, not only that, and also we verified a bending moment at any point. Mx equal to minus EI d square by dx square. We got another expression for bending moment. We got solution, no W. Please let me to finish. We got the solution W equal to this one, no. You differentiate this twice, okay, with respect to x. You differentiate this twice with respect to x. You'll be getting d square W by dx square. Okay, that's what. M equal to minus EI d square W by dx square. In that substitute by differentiating that twice. Okay, that is substituted here. Okay, therefore M max at x equal to L by 2, we are getting M max. So M max also I have calculated from this. Okay, I substituted x equal to L by 2 in this expression. In the mx expression, I got 4 p naught L square by pi cube. That is equal to p naught L square, pi cube divided by 4, 7.75. Okay, what is that bending moment for a simply supported beam subject to UDL? W L square by 8, you know, isn't it? Here it is p naught L square by 7.75. But exact solution Mmax is equal to W L square by 8, no? P naught L square by 8. We are getting almost same. Here 7.75, here 8. If you want to achieve this 8 here, what to do? You have to go for two terms approximation in the trial function. In the trial function, I have chosen only one term approximation. That is why I got a 7.75 only. I could not slightly closer to the 8 in the denominator. If I want to go closer to this 8, what to do? I have to go for three-term approximation. Is it possible for me to explain with the two-term approximation and three-term approximation, whatever calculation I have done so far manually? It may be very hard for you to do it manually. Okay, with the two terms approximation, three-term approximation, four-term approximation. If I do it with the two-term or three-term approximation, definitely I will be getting here P L square by 8, very closer to 8, 7.9 something I would have got. Okay, here also I would have got instead of 76.5, I would have got nearly 76.79 something, nearly 76.8, closer to that I would have got if I would have gone for two-term approximation. I hope you will understand. Okay, so that is the beauty of this method. See, that's the beauty of this method. I have also in my notes I tried with to get more accurate solution. Take one more term in the trial function. I have done this also. I have done. Okay, I have written. I have not done. I have written a1 sin pi x by L plus a2 into sin 3 pi x by L. I have chosen another function. Okay, next class I will continue. With this I will stop today discussion. I will continue in the next class. Okay, I want to record your name for attendance. See, very good. All of you are attending. Always M.Tech students are very sincere students, right? 1 minute. Just I am recording your name for attendance. No, just for record, not for attendance, just for record purpose. Just I want to record your names. Okay. Good. So I will stop with this one. Okay. So bye to all of you. Thank you for your listening. Okay. Bye. So I will stop recording. Right. Stop recording. Stopped it. Bye.